In this video, we'll learn about one-dimensional motion when acceleration is constant. When we have one-dimensional motion and an object moves with constant acceleration, the instantaneous acceleration at any point in a time interval is equal to the value of the average acceleration over the entire time interval. So when acceleration is constant, we have three of the following equations, where we have our final velocity is equal to our initial velocity plus our acceleration times time. Our displacement is equal to our initial velocity times time plus 1/2 times acceleration times our time squared. And our final velocity squared is equal to our initial velocity squared plus 2 times our acceleration times displacement. Let's see how we can use the equations that we learned in our prior slide and see how we can apply them to our problems below. And our first problem, it states that a race car starting from rest accelerates at a constant rate of 5 meters per second squared. What is the velocity of the car if it has traveled 100 feet, and how much time has elapsed? First, if we start with summarizing the information we're given, it says that the car starts from rest, so the car's initial velocity is 0 meters per second and accelerates at a constant rate of 5 meters per second squared. So our acceleration is equal to 5 meters per second squared and has traveled 100 feet, so our displacement is 100 feet, and we're asked to solve for the final velocity of the car, which is unknown, which is what we're trying to solve for. So first we see that our initial velocity, our acceleration, are in meters per second. However, our displacement is in feet. So first we must convert our displacement of 100 feet into meters. So for 1 meter, there are 3.28 feet in 1 meter. So if we divide this out, we see that our feet will cancel, and our displacement in meters will be 30.48 meters. So now that we have all our information in meters and seconds, we can solve for our final velocity. One equation we have where we can solve for final velocity is our final velocity squared is equal to our initial velocity squared plus 2 times our acceleration times our change in our displacement. Since we're trying to solve for our final velocity, we can get our final velocity by itself by taking the square root of both sides. And when we do so, our final equation will be the square root of our initial velocity plus 2 times our acceleration times our change in our displacement. If we plug in the values we have for our variables, see that our initial velocity was equal to 0 plus 2 times our acceleration of 5 meters per second squared times our change in displacement of 30.48 meters. And when we multiply this out, we'll see that our final velocity is equal to the square root of 304.8, and when we take the square root of this value, we see that our final velocity will be equal to 17.5 meters per second. Now that we solved for our final velocity, now we're asked to solve for how much time has elapsed. So in part B, we're asked to solve for time. So one equation that we learned is that our final velocity is equal to our initial velocity plus our acceleration times time. We solved for our final velocity in part A. We know our initial velocity and our acceleration was given to us. So if we rearrange the equation to solve for t, we'll see that our final velocity minus our initial velocity divided by our acceleration will give us time. If we plug in the values we're given, our final velocity was equal to 17.5 meters per second minus our initial velocity of 0 meters per second divided by our acceleration of 5 meters per second squared. And when we do so, we see that time is equal to 3.5 seconds. In problem 2, we see we have a jetliner that lands at a speed of 160 miles per hour and it deaccelerates at a rate of 10 miles per hour per second. If the plane travels at a constant speed of 160 miles per hour for 1 second after landing before applying the brakes, what is the total displacement of the aircraft between touchdown on the runway and coming to rest? So, like we did in our first problem, let's list the information that is given to us. We know that our initial velocity is equal to 160 miles per hour and that our final velocity will be 0 since the plane is coming to a rest. And we're given our acceleration, which is negative 10 miles per hour per second. We see that our acceleration is a negative value because in the problem it says the plane is decelerating. Yeah, again, our units are given in miles and hours. So let's convert our miles into meters. So we're getting 160 miles, and to convert it into meters, we know that in 1 mile there is 1,609 meters. And so our miles will cancel out, which will leave us in meters. And now, if we convert hours into seconds, we know that in 1 hour there are 60 minutes, and in 1 minute there are 60 seconds. So our minutes will cancel out, as well as our hours, and we will be left with meters over seconds. When we multiply and divide this through, we'll get an initial velocity of 71.5 meters per second. So we just got done converting our initial velocity of miles per hour into meters per second. And now if we convert our acceleration of negative 10 miles per hour per second, we can convert into meters per second squared. So we know that for 1 mile, there are 1,609 meters for every 1 mile. So we see that our miles will cancel out, which will leave us in meters. And to convert our hours into seconds, we know for every 1 hour, there are 60 minutes. And for 1 minute, there are 60 seconds. So we see that our hours will cancel out, which will leave us over meters over seconds times seconds, which will give us a unit of meters per second squared. So when we multiply and divide this out, see that the value we will get will be equal to negative 4.47 meters per second squared. So we see that our plane coasts for 1 second before applying the brakes. So during this 1 second, our change in displacement will be different while it's coasting than when it's braking. So first we must solve for our displacement when the plane is coasting. We have an equation where our change in displacement is equal to our initial velocity multiplied by times plus 1/2 our acceleration multiplied by our time squared. And we can plug in our values to solve for our change in displacement, since we know that our initial velocity is equal to 71.5 meters per second over a period of 1 second plus 1/2 our acceleration, and since the plane is coasting, our acceleration will be 0 multiplied by our time squared. Our acceleration is 0. We see that this part of our equation will be equal to 0. So our change in displacement when the plane is coasting will be equal to 71.5 meters. So now we found out the displacement of the plane when it's coasting. Now we must find out the displacement of the plane when it's applying its brakes. So an equation we can use is our final velocity squared is equal to our initial velocity squared plus 2 times our acceleration times our change in our displacement, which will be braking in this case. If we rearrange the equation to solve for our displacement, we see our final equation will be our final velocity squared minus our initial velocity squared divided by 2 times our acceleration. And if we plug in the values we're given, we see that our final velocity will be 0 since it's coming to a complete stop, and that our initial velocity was 71.5 meters per second squared minus our initial velocity of 71.5 meters per second raised to the second power divided by 2 times our deceleration of 4.47 meters per second squared. And when we multiply and divide this out, we see that our change in displacement when the plane is applying its brakes is equal to 572 meters. And we're asked to solve for the total displacement. And so our total displacement will be equal to our displacement when the plane is coasting plus our displacement when the plane is applying its brakes. So we plug in the values. The displacement of the plane while it's coasting was 71.5 meters plus our displacement when the plane is applying its brakes of 572 meters is equal to 643.5 meters. So it takes the plane 643.5 meters to come to a complete stop.